All right, now this is section 3. For section 3, we are dealing with greatest common factors. So, for this first scenario, Mr. Ellis is in charge of an after-school program, and he's got 56 9-year-olds and 42 10-year-olds, and he wants to divide them or break them up into equal groups, all right, to be able to make basketball teams. So in order to do this, we have to, one way to do it is to list all of the factors of 56 and then list all of the factors of 42. And then we're looking for the factors that are the same in both. And as you can see, Mr. Ellis can make one big team, two teams, 7 teams, or 14 teams. So listing the factors is one way, but a lot of students have difficulty finding that 14 was a factor of both of those. So you can use the prime factorization to find the greatest common factor. And when we're doing that, we make a factor tree if we need to, and then we look at the prime factors that are the same. Both of them have a 2, and both of them have a 7. Okay? So then we take 2 times 7, or the prime factors they share, and that's our greatest common factor. So the greatest number of teams that Mr. Ellis could make would be 14 teams. Then if you think about that, if he made 14 teams, then there would be 4 9-year-olds on each team, and then there would be 3 10-year-olds on each team. Okay, so if I add those two together, it would be 7 people per team. Okay, and then part C is asking, do you think that he should make the greatest number of teams? Okay, I said yes. I think Mr. Ellis should divide um, all of the children into 14 separate teams, and here's why. Um, it makes the most amount of sense. First of all, one big team's just not going to work. Kind of have all 98 of them go, okay, here, go play basketball. That won't work. And two big teams, there's just too many kids to be able to play basketball. 7 teams would work, but that's an odd number of teams. And with it being an odd number of teams, you'd have one team that would be sitting out, which might be all right, but I could see that being bad as well. If it doesn't last for so long, you want all the teams playing if you can. So 14, because it's an even number of teams, everyone would be in a game at the same time. So dividing the children into 14 teams makes sense. Notice this answer. Notice that I'm not just writing down yes and no. I'm not just writing down yes because that and be done with it. I'm really going through and explaining it. Yes, Mr. Ellis should divide the children into 14 teams instead of 1, 2, or 7 teams. Does not make sense to have one big team, and 2 teams would mean too many players on each team. The number of players on each team is more reasonable if there are 7 teams, but then one team will not have another team to play. So dividing the children into 14 teams makes sense. Clear, complete sentences, easy to understand if somebody else is reading my explanation. Okay? These homework pages aren't too many problems. You should take your time and do a good job on them. Part D says out of the 9 and 10-year-olds that are there are 28 9-year-old girls and there's 27 10-year-old girls. And so can Mr. Ellis go and make sure there's an equal number of girls on each of the teams? So listing the factors, of 28, breaking up the 28 9-year-old girls and breaking up the 27 10-year-old girls, you see that the only factor that is the same is 1. So Mr. Ellis cannot make teams with an equal number of 9 and 10-year-olds and an equal number of each aged girl because 56, the number of 9-year-old children, 42, the number of 10-year-old children, 28 and 27 do not have a factor in common other than 1. So the only way we can get them into equal groups is if we just take one big group. Notice how all of these problems are about breaking them up into smaller parts or dividing them into smaller parts. Whenever we're finding the greatest common um, factor, we are always dividing into smaller parts. Now for number 2, notice how they went from A, B, C, D to a number 2, so a different type of problem a little bit. They're taking care packages and they're breaking up the different parts of the care packages to be sent out. So we could find the greatest common factor by doing prime factorization. So I'm doing a factor tree for the 30 decks of cards, the 150 sets of stationery, like paper and pencils, and the 75 crossword puzzle books. Then after I do the prime factorizations of these three, I'm looking for prime factors that are the same. So all of them don't have a 2, so I don't write down a 2. All of them do have a 3, so I write down 1 3. All of them have at least 1 5, so I write down 1 5. So 3 times 5 is 15. So the students, the class, are going to be able to make 15 care packages with an equal number of each item of each with an equal number of cards, stationery, and crossword puzzle books, and at the same time not leaving anything left over because they don't really want anything to be left over. Number 3, I've been asking number 3, do you have a preference? And you guys have been answering that pretty good. Okay. Ooh. All right, so this is the 4th section. The first question is, how do you know when to use common factors and when do you know how to use common multiples to solve a problem? When I know I'm using the GCF, or the greatest common factor, or common factors, when I have to divide things equally or put them into equal groups. I know that I'm looking for the least common multiple or common multiples when something happens in cycles or something keeps occurring or something's getting larger. Multiples indicates that I'm going to multiply, okay? And then greatest common factors, I'm usually dividing if I'm thinking of math operations to go with each of those, okay? Number 2 deals with Mr. Chalky, and he's a groundskeeper, and then there's sprinkler systems, and there's 3 zones. And with the 3 zones, one goes every 90 minutes, zone 1. Zone 2 goes every 40 minutes, and then zone 3 goes every 45 minutes. If I read this one carefully, it says list the times. So if you listed the multiples of 90, 40, and 45, that's okay. But I listed the times that these sprinkler systems would go off in the different zones. So zone 1 would be 12 o'clock, 1:30, 3 a.m., 4:30 a.m., and 6 a.m. Then zone 2, I'm just counting by 40 minutes. And I'm being careful that I am counting correctly with hours and all of that. So got 12 a.m., 12:40, 1:20 a.m., 2 o'clock a.m., 2:40 a.m., 3:20 a.m., 4 a.m., 4:40 a.m., 5:20 a.m., 6 a.m., and 6:40 a.m. All right? And I'm remembering, I'm just going until 7 a.m., or that would be 7 hours. Or if I was doing this in minutes, I would go until I got to 420 minutes, because that would be 7 hours worth of time. So zone 3 goes off every 45 minutes. So these are the 45 minutes going all the way through to up to 7 o'clock, and you can see those. So what I'm looking at here is I'm looking at the times when all of the sprinklers would be going off at the same time. And all of them are only going to go off just once in all three zones. And they're all going to go off in all three zones just at 6 a.m. Notice how there's two questions there. It says how many times are they all going to go off, and then what time. And you can see that 6 a.m. is in all three of them. There's several that are just in two, but 6 a.m. or 360 minutes is just once. Part C is asking how many minutes after midnight will all three zones turn on at the same time. Notice how this was cycle problems. This happened every so often, so this is the least common multiple problem. To do this, I decided to show the least common multiple by doing the prime factorization. All right? And so I did the prime factorization for 90, and then I'm going to do the same thing for 40, and then I'm going to do the same thing for 45. I'm just going back to check the numbers as I'm going through and making sure the colors are the same then too. So I do my prime factorization. Notice how I always write out what the prime factors are at the end. I write the mathematical statement to go with that. All right, that's to make sure I'm clear on what I wrote. Okay. Then now for the least common multiple, I'm first going to write down every base that I see. And if I look, I see there's 2's, there's 3's, and there's 5's. So I'm going to make sure I write in there that there are 2's, 3's, and 5's. Then for the least common multiple, I look for the biggest exponent for each base. For 2, the biggest exponent is 3. For 3, the biggest exponent is 2. For 5, the biggest exponent is, well, 1. So I leave it as it is. Then all I do is I multiply those numbers together. 2 to the third power is 8. 3 to the second power is 9. And then 5 stays down. And that's going to equal 360 minutes. So all three are going to go off at 360 minutes. Essentially what I've done is in part A, I've kind of listed the multiples. And in part C here, I've done the prime factorization to find the least common multiple. Okay. For D, it says, Mr. Chucky has learned that the resort's guests have complained early in the morning when all three sprinkler systems are going off at the same time that when they take a shower they don't get any pressure. Okay? Well, there's several things you could write here, but the two main things are Mr. Chucky could change one of the cycles, the amount of time in between the sprinklers going off, and he could change one of those so that the least common multiple is greater than 420. Why 420? Because there's 420 minutes in 7 hours from 12 a.m. to 7 a.m. during the times that the sprinklers are going off. So he could make sure that the first time all three would go off at the same time would be well after they're shut off for the day. His second option is he could just turn off the sprinklers right before 6 a.m. because 6 a.m., 360 minutes, is when all three sprinkler systems do go off at the same time. So he could just shut them down at 5:55 a.m. or 5:59 a.m. to make sure that all three sprinkler systems aren't being run at the same time. Okay. Notice how I'm trying to explain this in complete sentences. I'm trying to explain it in more than one way if I'm able to. I'm trying to make sure my answer is clear as I'm going through this. For part E, it asks you to write your own word problem